Well, hello everyone. My name is Orlando Hernandez. I am with the Department of Electrical and Computer Engineering at the College in New Jersey, in Ewing, New Jersey. And as was mentioned, this is a presentation of an architecture for computing the Markov random field parameters. The motivation for this implementation is in the context of a computer vision system that can process high quality video at real time at high frame rates. So it is scalable in the sense that it will fit into a high performance clustering algorithm, which is not the topic of the paper, but this is the context of the feature extraction. And then the features, this hardware is scalable in that we can trade off power and frame rate versus how many of these cells we use per frame, how many replication of the hardware. So what we are looking here is specifically at this cell that we would use to extract the features from a frame. The Markov random field model is predicated upon a random observation of a field or a neighborhood of pixels on windows in a frame. So the observations are expected values of this random field. So the parameters that we are looking for, if these two equations here or these three equations describe the Markov random field formulation, we are looking for the estimation of the thetas and the estimation of the rho, and that makes our random field, Markov random field parameters that can be used then to synthesize the picture, the pixel values in a texture. So this features works well for texture capturing and representation. So these last two equations here are the estimates of the thetas formulated as matrices, and even though in this work, as I'll show later, we have used color pictures or frames to prove the architecture, for the implementation of the hardware, it has been projected, the color field has been projected to grayscale for simplicity of the implementation, although we can envision more complex and higher power architectures if we work with the color representations, and instead of matrices, then we will have tensors that are deep by the color model. Also, we will have the ability to eliminate illumination variances by simply dividing the color model by the highest intensity color. So essentially, the architecture is going to follow the implementation of these two equations here, and I have that in a couple of diagrams where we start with the values of the pixels and we start forming the matrices and the multiplication of the matrices in this section over here of adders and multiplier arrays, and then of accumulators. So by the end of this part of the hardware, we have this part of the equation. So going back, this part over here formulates the one part of this equation over here. And then we have another section where we keep processing the values and forming the matrix manipulation and accumulation. So at the end of this part here, we have the accumulation of the Q matrices and the transpose of the Qs. So that again goes back to this part of the equation, this accumulation over here, and the appropriate scaling. So by this time in the architecture, we have the thetas that calculated, which we can use to then calculate the rows. So in the second part, we have the thetas that propagate down to give us the final results. But then in this section over here, we are essentially working on that second equation that is shown. So by the end of this part of the architecture, you can see over here, we have this part of the equation, and then we accumulate that and scale, and then we will have our raw estimates over here. So onto the results. We have the results of the hardware that it takes, the delays. We implemented this into an FPGA, and we were able to achieve a processing speed of about 6 megahertz and with under 6 watts of power. And this is a picture of the floor plan, the actual floor plan, and the layout in the FPGA implementation. So specific to the results, we looked at 4 very different textures in color that again were projected to grayscale. We have wood, fir, water, and moss. And then for the purpose of looking at the specific, what the implementation actually yields numerically, and remember that we are going to be comparing this to a software implementation of floating point versus what we have, which is a fixed point implementation. So we're going to be comparing the error of those two implementations. So we have extracted the windows, which are 8 by 8 pixels from one of these textures, and then we have derived the micro-random field parameters from software, and then use that to reconstruct the textures. So just that window for the purposes of illustrating the work here. And this is the reconstruction by software, and this is the reconstruction by using the micro-random field parameters, the thetas and the rho from the hardware implementation. And we can see that they're visibly very similar, but also we computed these are the actual parameters in floating point format after we got them in fixed point for the hardware implementation. This is the software actual parameters for each of the textures, and then we computed the errors between the software and the hardware implementation. So taking the software implementation as the reference. So these are the actual errors that we obtained for each of those 4 samples. From a system level performance, if we were going to work with a frame size of let's say 576 by 702 pixels and at 60 frames per second, we only need to process for that window at about 379 kilohertz. So the fact that our architecture works at 6 megahertz allows us for trading off frame rate and the number of hardware or parallel hardware realizations that we have to use to process a given video stream. So in conclusion, we think that this is a high performance VLSI architecture for the computation of the micro-random field texture model parameters, conducive and scalable for computer vision. And the accuracy and the performance we think is comparable to the software-based implementation, which is the reference. We did implement this into an FPGA and simulated and proved that the actual architecture can sustain DVD quality frame rates for MPEG-2. And again, this has applications for unsupervised learning algorithms, for different types of clustering algorithms, but also for supervised learning using deep neural networks and other type of machine learning approaches. And again, it is applicable to military, industrial, as well as commercial applications that require real-time intelligent machine vision processing at high-quality video. So this is the conclusion of our presentation. So if there are any questions, I'll be happy to answer those.
Yeah, Orlando. Any questions? We have sufficient time for questions. For wrapping it up here soon. No questions. Maybe some might come a little later, so we can leave it offline. So Orlando, thank you for your interesting talk. So we will move on to the next.
But thank you very much. I will stop sharing at this point.